All right, guys, it is 10/29/2020. We are now going into breaking up. We're now going into acid-base chemistry and oxygen and CO2 transport. We just completed the pulmonary mechanics exam. For the most part, I'm very, very pleased. Had a lot of A's, B's. If you didn't do as well as you thought, that's okay. You're still in good shape. Come to tutoring when you need to, and then we'll be fine. Okay? Tutoring is every Tuesday and Thursday from 2 to 4 on Zoom. Okay? On Zoom. Now, when you come to tutoring, if you need tutoring, you always just, already be planned to know what you want to do. That way it's not just because it's not a teaching session, it's tutoring you for what you need help with or what you're not comfortable with. Okay. All right, so we're going to start acid-base chemistry, but I will go over the exam right quick so we can get an understanding of what you might have done. Like I said, it's not many people. Everybody did fairly well. Let me go to it right quick. I'm going to go through it really quick. All right, number one, the normal ratio for ventilation to perfusion is 4 to 5. Given a tidal volume of 500, dead space of 150, respiratory rate of 12, the alveolar minute ventilation should be, I think that's 4.2. I have to get my calculator out. 4.2, okay. 4.2, what you do is you just, you have to do for alveolar minute ventilation, you have to take tidal volume, subtract the dead space, right? So that'll be 500 minus 150, and then you multiply that by the 12. Number 3, what is the normal RQ? Respiratory quotient is 0.8. The normal value for inspiratory capacity, IC 36, right? Number 5, true shunts are refractory to what? Should have been oxygen. Said true shunts or absolute capillary shunts are refractory to oxygen, means they do not respond to oxygen. Number 6, which of the following devices is used to measure the minute ventilation? We said it's the Wright's respirometer. There are other types of respirometers, but that's what you would use. Number 7, the maximum, and I even went and highlighted this part today because it wasn't highlighted, but the maximum amount of air that can be breathed in and out is your vital capacity. Vital capacity. Then this one had some letters, and you had to identify which letter that it asks. The F. What does the F represent right here? You have tidal volume, normal in, normal out, normal in, normal out. Then you have your ERV right here and your RV down here. So ERV and RV together is the FRC. That is the FRC. All right, the volume, which volume is not in vital capacity? Remember, vital capacity is everything that you can do. And so what you can't do is RV. Okay? Like my daughter would say, what you're not going to do is residual volume. Okay? Changes in FRC are indication in changes of compliance. Compliance. We said FRC and compliance are directly related. Okay. Number 11, the inspiratory capacity consists of which of the following? Which one of these is inspiratory capacity? Should be tidal volume and IRV. So 1 and 2. IRV and the tidal volume together make your inspiratory capacity. All right, the gas left in the lungs during a quiet exhalation. Left in the lungs following a quiet exhalation is your FRC. After you exhale normally, you still have ERV and RV in your lungs. Okay. Number 13, which type of shunt is considered a true shunt? That would be absolute. 14, the formula to determine alveolar minute ventilation is frequency times tidal volume minus dead space. Right here, frequency times tidal volume minus dead space. 15, if the tidal volume and frequency remain constant, then an increase in dead space will cause a decrease in alveolar minute ventilation. 16, which of the following increases compliance? Which one of these would increase compliance? We said compliance is synonymous with FRC. It's also synonymous with COPD. So which one of these diseases would be COPD disease? The only one is emphysema. So if I have emphysema, I'm going to have a higher compliance and a higher FRC. What about my elasticity? Will that be higher or lower? The elasticness. Lower, good, lower. The elasticity is going to be low because it's floppy, right? Old draws. All right, 17. Poiseuille's law says that if the diameter is decreased by half, increase resistance by 16 times. If you didn't have the picture, it really didn't matter, as long as you know the formula or the law, as long as you knew the theory or the law, what they call it, his law, 16 times. 18, shunting can be caused by which of the following? What can cause a shunt? Now we got to remember, a shunt is more blood than it is air. So which one of these things can cause more blood and less air? Well, decrease in ventilation, no. Increase in ventilation, well, I mean, sorry, decrease in ventilation, yes, that's one of them, right? Because you got more blood than you have air. So if my ventilation goes down, then yeah, that can cause that. So 1. What about an increase in ventilation? No, that wouldn't be it, because the definition of shunt is more blood and low ventilation. Number 3, a decrease in perfusion? No. Increase in perfusion? Yes. If I have increase in perfusion, then I am now pushing more blood. My perfusion has escalated. So now I have high perfusion and low ventilation. So it should be 1 and 4. 1 and 4. Decreased ventilation, increased perfusion. Number 19, which of the following volumes or capacities cannot be measured by simple spirometry? Anything that has RV in it, guys, you cannot measure it with simple spirometry. So that will be FRC and RV, because FRC has RV in it. Okay, so you can't measure it. So 1 and 3. And number 20, alveolar unit that has no perfusion but has great ventilation is a type. What type of unit? Dead space unit. No perfusion but great ventilation. Wasted. All of that ventilation has been wasted. Okay. All right. So that is the exam. Hopefully you saw what you did to make the mistakes that you made, and you can correct them. Now let's go into the presentation for today. Lesson acid-base chemistry. For a few objectives. During this lesson, the student, let me make it a little bit bigger. Student will be able to discuss 2 ways that oxygen is carried, applying Henry and Graham's law. There's 2 more laws that you're going to have to put down. That's why I say when you have your law sheet, have you a formula sheet, right? That way, anytime you learn a new formula, add it to that sheet. Okay, and anytime you heard a new law, add it to your law sheet. So when you start studying for the final, you don't have to search through all of the different sections trying to find that one law. You just have a straight up sheet of paper in your notes that have all the laws, and that's how you study them. Okay. So we want to know how oxygen is carried, because oxygen, you inhale it, but how does it get in the blood, right? How does it actually transfer into the blood and get down to my body, right? That is what you're going to learn today. There's 2 ways oxygen is carried. Give necessary information to calculate the dissolved, combined, and total oxygen content. The oxygen content in our blood, some of it is dissolved into the plasma, some of it is carried or combined to the hemoglobin, and some of it, and then when you add those 2 together, that's the total. So some of it is dissolved, and some of it is combined to the hemoglobin. And then if you add those two together, that's my total content, okay? Discuss and affect oxyhemoglobin saturation curve. The oxyhemoglobin saturation curve and the factors that influence it. That is, hemoglobin becomes a personified, okay? We personify hemoglobin. And I usually say she likes CO2 way more than she likes oxygen. She has an affinity. That's the curve called the oxyhemoglobin affinity curve, okay? Affinity means love or like for something. And so hemoglobin loves CO2 20 times more than she does oxygen. But she really, really loves carbon monoxide because she loves him 200 times more than she does oxygen. So I always look at it as, I look at the stuff y'all watch on TV. Just think about if oxygen is the good guy, right? And hemoglobin is with him for right now. And when CO2 come around though, she let go of oxygen because she really likes CO2, okay? But carbon monoxide been locked up, okay? And when he get out, everybody got to go, all right? That's how you look at it. And you can look at it male, female, however you want to do it. No disrespect, any kind of way. I'm just trying to help you understand and remember it better, okay? When carbon monoxide is on deck, everybody got to go. Oxygen got to go and CO2 got to go, okay? Because she loves carbon monoxide 200 times more than oxygen. That's why people die of house fires, because of carbon monoxide poison. Hemoglobin will shake off oxygen and pick up all the carbon monoxide in the room and will not carry any oxygen. And that's why you die of hypoxia. Okay? All right. So to keep that in perspective, most people who die in house fires die from the smoke before they ever get burned. Okay? I guess that's a good thing, so that, you know, at least you didn't die from being burned up. You know, if you're in a house fire, the smoke overcome you, you die. Okay, then you get burned up. So I don't know, either one is bad, but I'm just saying I guess that's better than being burned alive. Okay. Then you're gonna learn how to discuss and affect the, oh, I did that. Calculate the alveolar air equation. That's the famous equation for respiratory. That's the one I told you is the P big A equals FiO2 times P bar minus the pressure of water minus the pressure of carbon dioxide in the artery divided by the RQ. That's the big equation. You're going to learn that equation. It's not as much as you think. As long as you know the equation, just plug and pick. There you go. Okay. Discuss causes of hypoxemia and responses. Hypoxemia is a lack of oxygen in arterial blood. There's two different terms. Hypoxemia is the lack of oxygen in the blood. Hypoxia is lack of oxygen in the tissues. Okay. Differentiate the 4 types of hypoxia. So there's 4 types and their results. There's 3 ways that CO2 is transported, because CO2 also has to be transported. You're going to be able to describe the Haldane effect on CO2 transport, describe hypoventilation, and eucapnia, which you should already know. Hypercapnia, hypocapnia, or eucapnia is just either high, low, or normal CO2. Capnia is CO2. Describe the Henderson-Hasselbalch equation. List the buffer systems and their effects, and then list the normal ranges for ABGs. Describe given ABGs as respiratory or metabolic. If it's a CO2 problem, it's a respiratory problem, because CO2 is AKA respiratory, AKA acid, AKA ventilation. Remember I taught you that? This is where it comes into play. Okay, this is where it really comes into play. So you're going to know either the ABG is alkalemia or acidemia. Alkaline is base, like real basic, like rolling. You're looking at either what's something that a lot of that will give you indigestion, like pizza or Takis, right? them hot chips and all that, those will really give you some indigestion. And if you have indigestion, you take Rolaids to put on top of that. Those are very alkaline medicine. It bases it, it kind of buffers out the acid and makes you come back even, okay? So that's what's going on in your blood, okay? You're going to be able to tell me if that pH has been compensated, non-compensated, or is it partially compensated, all right? Number 14, discuss stimulation of the central and peripheral chemoreceptors. Central and peripheral chemoreceptors. We touched on that a little bit with pulmonary AMP, but now you're really going to hit it hard, okay? Discuss the normal control of ventilation and abnormal control of ventilation, all right? All right. Here we go. Oxygen transport. Let me new share the PowerPoint. All right. Acid-base chemistry and O2, CO2 transport. Oxygen transport. Oxygen is carried two ways. The first way, it's either dissolved in the plasma. The first way oxygen is carried is dissolved in the plasma. And that's using Henry's law. It says that the weight of a gas dissolving into a liquid is proportional to the partial pressure of that gas. Okay? That's what Henry says. Henry says that the weight of the gas dissolving into a liquid is proportional to the partial pressure of that gas. Okay? Uses the solubility coefficient for oxygen. Here it is. The solubility coefficient for O2 is this. It says that, and you don't have to remember this whole thing here, but it's just saying that 0.0023 milliliters of oxygen can be dissolved in 1 ml of plasma at 37 degrees Celsius and a barometric pressure of 760 millimeters of water. Okay? I mean, millimeters of mercury. I don't know why I said water. Millimeters of mercury, mmHg. Why 37? Why is 37 significant? Because that's normal body temperature, okay? You're going to learn that temperature, guys, affects many things in our metabolism, in the way our body does what it does. Temperature is crucial. If the temperature is really high, things change. If the temperature is really low, things change. No matter if they're talking about the solubility of oxygen into the blood or the humidity, how much humidity or water pressure, vapor pressure is in your lungs, okay? All that matters. So we always say, when we have true statements, we'll say at 37 degrees Celsius and 760, the barometric pressure. So 760 is the barometric pressure, or the P bar, okay? At 760 is the barometric pressure at sea level. So what we're saying is at sea level, and Memphis is pretty much at sea level. At sea level, the pressure of everything in the atmosphere is 760 millimeters of mercury, okay? Now let me show you that right quick. Well, before let me finish this up. This allows us to determine the amount of oxygen expressed in milliliters that is dissolved in the plasma. Now this is the formula that you must remember. The formula for dissolved oxygen into the plasma is 0.003 times the P little a O2. The P little a O2 is the partial pressure of arterial oxygen. Little a is arterial, right? So the partial pressure of arterial oxygen, that result comes from the ABG. When you stick your patient and it gives you these values, you'll pull the PaO2 out of there, multiply it by 0.003, and that's how many mLs have been dissolved in that patient's plasma. That's how many mLs of oxygen that is dissolved, okay? So what they're saying is that a PaO2 of 100 millimeters of mercury, exactly 0.3 mLs of oxygen is dissolved, okay? So that's the first way oxygen is carried, dissolved in the plasma. Dissolved in the plasma, and the formula is 0.003 times P little a O2, okay? And there's a link here. You can link. I think it'll take you to YouTube, and it'll show you something about dissolved in plasma. Okay, oxygen that's dissolved in plasma. All right, Graham's law. Graham's law is another law. Graham says that the rate of diffusion of a gas is directly proportional to its solubility coefficient and inversely proportional to the square root of its density, which you don't have to remember that whole statement. Just know that Graham's law talks about how he's talking about the rate of diffusion. So let me go to this. Graham's law is talking about how fast oxygen can diffuse, okay? And he's saying that he's about to show you that oxygen can diffuse fairly quickly, but carbon dioxide diffuses 20 times faster than oxygen, and carbon monoxide diffuses 200 times faster, right, than oxygen. So that's important, and that's telling you that hemoglobin loves CO2 more than it does oxygen, 20 times more, because CO2 can go across the membrane 20 times faster than oxygen can. And then when carbon monoxide is in the air or in the system, it diffuses across the membrane 200 times faster than oxygen. Okay, so that's what Graham is saying. He's just simply trying to show you the rate of diffusion. How fast can that oxygen travel from the alveoli into the bloodstream? Okay, oxygen goes in at a regular rate, but CO2 goes in 20 times faster, and carbon monoxide, which is CO, carbon monoxide is CO, it diffuses 200 times faster. Okay, so there's something I want to show you on the board right quick. Let me go back to where I was at, because something I was going to do before that page. All right, dissolved in the plasma. 0.003. Okay. Oh, yes, the barometric pressure. So to understand, because I told you, barometric pressure is 760 millimeters of mercury. So you want to, okay, well, where does that come from? Where does that pressure come from? Because millimeter mercury is a pressure, correct? And so is centimeters of water. So let's see where that pressure comes from, so you can understand. Go into your note-taking guide and see what the list of the percentages of stuff in the atmosphere, maybe on the next page or page after that. If not, I'll pull it up on the computer. Where it says oxygen is 20.9%, argon. Not on that page, not that thing, in your note-taking guide. If it doesn't, I'll find it on here, because it might not even, it might be a little far down. I'm trying to switch over to where I can get to the percentages in the atmosphere right quick, guys, so I can show you. Must be pretty far away. One second. Find this right quick. Might even be in the next section, but I want you to get a good understanding of this. Yeah. Never mind. I think it's in the next lesson. But to understand what 760 is, which is the barometric pressure, I need you to see what I'm gonna do on the board. So I'm just gonna stop share, and you can see what I'm doing on the board. All right, 760. Where did we get that barometric pressure? Barometric pressure at sea level is 760 millimeters of mercury. Okay, and so I'm gonna show you right quick where we got that from, and then we'll go on. So you need to have it in your head, so when we're doing the alveolar equation, you'll know why that's being used. Now, because I told you before, there's a difference between the percentages in the atmosphere. We have several different gases in the atmosphere. All right, several different. I'm going to show you where that 760 came from. All right. In the atmosphere is 21% oxygen, 78% nitrogen. I think it's 0.03% CO2. I'm trying to find know for sure. Argon and trace gas. All right, let me pause the video so I can find it, because you got to, I don't know why they don't add it there, but you really need it. All right, guys, this is coming up on the next lesson, which is gas physics, but I just want to show it to you right quick so I can show you where that 760 millimeters of mercury is coming from, okay? So once I write this on the board, then I'm going to get this off so you can see the board better. All right, so oxygen is really 20.95, but we go with 21. Nitrogen is 78%. Carbon dioxide is 0.03%. I was right on that. And then argon is what? 0.93% is argon. And then trace gases, that's, I call that the poops of the world, the farts, because that's methane, okay? Methane is what you poop out, all right? And so those are just small, 0. What? 0.1? Yeah, that's, you know, that's how small it is. That's trace gases. All right, trace gas. These are the gases, or gas of the atmosphere. All right. So it's on the board. You'll be able to see it on the board. Let me stop sharing so you can see me, because I'm the star. Ain't that right, Mr. Ritter? All right. So how does this come up to 760? Because when you add the percentages up, they should add up to about 100%. Okay, because that's all of the air. When I add these percentages, I get about 100% of the atmosphere. Okay, but these percentages, just like the gumbo I talked about, if I pull one out, it has its own flavor, or it has its own pressure, okay? Each one of these gases exert a pressure in your lungs, okay? Around you, against you, okay? That's why if you go into like deep underwater, the water gets heavier, right? Because if you go lower in altitude, you get more atmospheres, right? All of this is one atmosphere, okay? So these exert a pressure of 760 millimeters of mercury, which is 1 atmos. That's what they do. 1 atmosphere. Okay? 760 is 1 atmosphere. If you go down really low, you get this times 2. 2 atmospheres. 3 atmospheres, right? And the more atmospheres you go down, the heavier each one of these gases produce pressure, right? That's why we use hyperbaric oxygen therapy, because we put you in a hyperbaric chamber and bring the atmospheres down, right? Like that Kroger commercial when they say low, low, low. That's my favorite commercial. They bring the atmospheres down, okay? And when you do that, you increase the pressure that oxygen exerts, all right? So let's see what it exerts at 1 atmosphere like right now. Well, in order to find that, there's a formula that you have to say this times this. But you use this as a decimal. You change the fraction to, the percent to a decimal and multiply by 760. So the pressure of O2 is 0.21, because you got to turn it into a decimal. Anytime you turn a percent to a decimal, you move the decimal place 2 places to the left. Okay, just in case you didn't remember that. Whenever you change any any percentage to a decimal, you move the decimal place over 2 places to the left. So 21 is known to be 21, right? It's 21 point whatever, 0. So the decimal is always after the whole number, right? So when we're going to change this to a decimal, we have to move it. 1, 2. So that makes it 21%. Nitrogen would be 1, 2.78. CO2 would be, see, the decimal is already right here, okay? Because this is not even a whole number. So 1, 2. So then it would be 0.0003 when I multiply. See that? And then argon, see, argon already has a decimal in the number. It's already a decimal. So you don't come from here because it's already less than a whole number. So you say 1, 2, put it right there, and it becomes 0.0093, okay, as a number. And then trace gases, same thing. 1, 2, becomes 0.0001, okay? Now I can tell you how the pressure is. So 0.21, which is oxygen. We're doing the pressure of oxygen in the atmosphere. Notice I didn't put an A right here because I'm not talking about arterial or alveolar. Big A is for alveolar and little a is what? Arterial. So I'm just talking about the pressure period out here in the air. So 0.21 times 760 is what? 0.21 times 760. 159. So the pressure of O2 in the atmosphere is 159 millimeters of mercury. See that? That's the amount of pressure that oxygen exerts in the atmosphere. It's 21% of the atmosphere, but it exerts a pressure of 159 millimeters of mercury. Okay? So with that being said, what is the pressure of nitrogen? This is the formula here. You have to do whatever you're looking for times 760. So we've already made nitrogen a decimal. So what would nitrogen be? 592. 592 millimeters of mercury. See how much stronger nitrogen is? Nitrogen exerts way more pressure than oxygen. And you're going to learn later why that is so. Okay? It's not a mistake. What about the pressure of argon? Pressure of argon would be what? And that's 0.0093 times 760. 0.0093. So we move that decimal. 7.06, which is the 7.06 millimeters of mercury. And then what about the pressure of CO2? Pressure of CO2, which would be 0.0003 times 760. Sounds good to me. Was 0.228. Yeah. 0.228 millimeters of mercury. See how small that is? And then finally, trace gases. The pressure of trace gases would be 0.0001 times 760. What you get? 0.076 millimeters of mercury. All right, so let's check our theory. Add these up, the ones with the red line on it, a pink line. Add them up, and you should get 760. If you might get a little bit less or more because we didn't do all of the decimal places, but you should get dang on close to 760. But these are all the pressures. We said the percentages add up to 100%. Well, their pressures should also add up to what the pressure is. Atmospheric pressure is 760. So when you add 159 plus 592 plus 7.06 plus 0.228 and plus 0.076, you should get really close to 760. All right, so 760. Because some of these had a little bit more on the decimals that we didn't add. Okay, so it comes out. These add up to approximately 760 millimeters of mercury. That's why so now you understand what that pressure, because if I keep on teaching, and this should have been in this lesson, but if I would have kept on teaching and talking about 760, like, well, what is the 760? Where does it come from? Why is it there? That's why it's there, okay? 1 atmosphere, it's called the barometric pressure. When we talk about barometric, you hear about barometric pressure, that's the pressure of all of the gases in the air pushing on, okay? Now, the reason why, what they say happens when you go to Denver. If somebody goes up high and okay, say you go up, say that happens, you go up in the mountains, your ears pop. What about when you go up into Mount Everest? Can you just sit there and breathe easy at Mount Everest? It's harder to breathe, okay? Because we talk about, why does air go into the lungs? Why does air go into the lungs? Speaking on a physics level, why does air even go? How can it go? What has to happen? Has to be a difference in what? Pressure. The lungs has to become less than outside, right? In order for the air to go in, okay? And so when you way up high, the nitrogen pressure is way lower. So it's oh, the air is thin up there. You know, you hear that word, the air is thin. It's not thin. It's just that nitrogen exerts less of a pressure. So you have to get really low in order for it to go in. So it's a harder pull, okay? You have to pull harder because in a higher atmosphere, the pressure is lower than 760, okay? Because nitrogen is much less up high, okay? And so it's not exerting its pressure like it's usually doing 592. I don't know what it is, but it's way less than that. And so now the barometric pressure is way lower at a higher altitude, okay? And so you got to get lower than that in order to get the breath, okay? So it's like limbo. How low can you go, right? If we breathing like this, I'm just breathing, no problem. 760, no problem for me to get lower than that, okay? But when I go up really high, the pressure outside is lower than it is right here. So now I got to get lower in order for it to come in, all right? So it's harder to breathe. It's like you're short of breath, struggling if you don't have a little assistance because the pressure is lower, okay? And so that's why. So that's why we want to know this, because when I do the alveolar air equation, you are going to have to understand what's all a part of the formula, okay? So that's that. That's how you find the pressure. That's how we got 760. All right, now we're going to take a break. You're going to take a break. It is 9:55. Come back at 9:55. Yeah, come back at 10:05. And we're going to move on, but I'm going to put up the alveolar air equation, explain what all the components are, okay? And then we're going to keep on with the lecture. Let me pause here. Okay, guys, we're back from break. We're going to knock out this alveolar equation, not into whole depths, but because we're not going to get too ahead of ourselves. But I do want you to understand what that barometric pressure was so that you can understand the alveolar equation, because you will do this in this section, the alveolar air equation. So, review. Big A means alveolar. Abbreviation for big A is alveolar. Little a means arterial. And P means pressure. Okay? Now, in our terms, pressure will be partial pressure. Okay? Partial pressure. So, P big AO2 is the what? Partial pressure of alveolar oxygen. The partial pressure of alveolar oxygen is P big AO2. Okay? What about this? What if I said P little a O2? Let's say it together. Partial pressure of arterial oxygen. What about this? What is that? Yes. Okay. That's part of 210A, right? The first test you took. That's why you have to know this stuff. Go back so you're not lost when you start seeing these abbreviations. Okay? So that's what we're about to talk about. Now, this right here, FiO2 is the fraction of inspired oxygen. FiO2 is the fraction of inspired oxygen. How much oxygen did they inhale? Okay? How much? What percentage of oxygen did they inhale? Now, what do we say the oxygen level percentage is in room air, in regular room air, right now? 21%. You're going to hear that a lot, guys. Room air. They're going to say, oh, room air. Room air means 21%. Because they're going to say your patient was on room air and this, and this, right? And you're like, well, what's that mean? That means that the oxygen that they're breathing in is 21%. Everybody in this building is breathing 21% oxygen, along with 78% nitrogen, along with argon, a little bit of CO2, and somebody proved it, so a little methane. Okay, little trace gas. All right, so the reason why we say that is because things change. The pressure of oxygen at room air is 159, right? We said the pressure of oxygen at room air, or at sea level, is 159 millimeters of mercury. But if I put some oxygen on your nose, now I am increasing the percent that you're taking in, right? And so that's going to increase the pressure that you're taking in. So what if I have somebody on, just really quick, if I know that 21% equals 159 millimeters of mercury, because of the formula we did, the 760, what if I got a person on 40% oxygen? What would be the pressure then? What would be the pressure of 40% oxygen? That's going to be a big difference. Remember, we said to find that you have to take, you have to do 0.40 times 760, right? Because we did to find the room air, we said 0.21 times 760 gave us 159. Well, if they're on 40%, it's 0.40 times 760, and it's what? 304 millimeters of mercury. So look at that. That's a big difference. If I got them on some oxygen, now the pressure of that oxygen in the body is 304 millimeters of mercury instead of 159. Okay? So that's why we give oxygen, because sometimes people have problems oxygenating. So we have to introduce a little supplemental oxygen, maybe a nasal cannula, a mask, and we go all the way to life support if we have to. Okay, we have a toolbox. Respiratory therapist has a toolbox, and you can pick what you need to overcome the hypoxia. Okay, you don't go straight, oh, you short of breath, lay down, let me put this tube down your throat. Right, you don't go all the way there. First, start low. You'll put a little nasal cannula in your nose. Put you on 1 liter, 2 liters, and let's see if that helps. If that don't help, we can go up, okay? We go into our toolbox and add a little bit more. non-rebreather, the one with the little bag on it, stuff like that, if you have to. But the reason why I'm showing you this is because FiO2 is the fraction of inspired oxygen. So if I have them on 40% oxygen, then the FiO2 is 40%. The FiO2 of room air is 21%. So this is the FiO2 right here, fraction of inspired oxygen. If I got them on 50%, then their FiO2 is 50%. Okay? And sometimes you'll see it like this, 0.4. FiO2 of 0.4, right? That's 40%. Because you know, if you move to change a decimal to a percent, you move the decimal 1, 2, 40%. Okay, just like I went from percent to decimal, I had to move the decimal 2 to the left. Where if I start off with a decimal and going to percent, I got to move it 2 to the right. Okay, those basic math things, you know, a lot of people forget because they ain't did that in God knows how long. Okay, all right. So let's move on with the formula right quick. So the P big AO2, this is the alveolar air equation. It's going to, when we get done and get an answer, it's going to tell us what is the pressure of oxygen inside the alveoli. Okay? I don't want to know nothing else. I just want to know the oxygen. So I have to subtract CO2 from it, subtract the water vapor away from it, all of that, right? And I'm going to be left with only the pressure of oxygen. That's all I want to know is the pressure of oxygen inside of this alveoli. Okay? What's the pressure in it? All right, so FiO2 times the barometric pressure minus the water, the pressure of water, the pressure of H2O is the pressure of water, okay? Because when you breathe in, we breathe in moisture because we learned in pulmonary A and P that what part of the body moistens the air? When we breathe in, what part gives us the humidity and heat? What part of the body did we say? There it is, the nose, the nose. Because it swirls around those nasal conchi, right? Goes in, swirls around, gets hot, picks up moisture, then goes down. Has to do that or the lungs cannot use it, okay? It has to be a certain amount of humidity and it has to be a certain amount of moisture, okay? Or heat. So that's why we say body temperature, stuff like that. Those things are important, right? So just so you know, the air at 37 degrees Celsius inside the alveoli. Let me say air in alveoli. The air or gas in the alveolus is 37 degrees Celsius. It is 44 milligrams per liter, and it exerts a pressure of 47 millimeters of mercury. You need to understand that, highlight that, understand it, remember it. This is a fact. The gas inside of your alveoli at body temperature should be, that's the goal. By the time it gets to the alveoli, it's 37 degrees Celsius. Let's hope everybody can see it. The air in the alveoli, right? By the time it gets to the alveoli, it should be 37 degrees Celsius. It is saturated with 44 milligrams of water vapor. And it exerts a pressure of 47 millimeters of mercury. Okay? That water vapor. The water vapor exerts 47 millimeters of mercury. Let me specify that. This is the water vapor. H2O vapor. Okay? That water vapor, which is 44 milligrams of water vapor floating around your lungs, that water vapor exerts 47 millimeters of mercury of pressure. Okay? It exerts its own pressure too. Okay? That is a true fact for the rest of your respiratory life. That is the true fact. And when we get to aerosol and humidity, you're going to learn this again, and you're going to see it more. You don't have to memorize this part for the test. All right, this is just some information to lead you to understand how we arrive at the volume or the pressure of the alveoli. Okay. All right, so alveolar air is 37 degrees Celsius. It is saturated with 44 milligrams of water per liter, and that water exerts 47 millimeters of mercury of pressure in the lungs. Right, so that's important to know. All right, now, so I'm gonna give you some values, and I want you to pull me out what we got. Okay, Mr. Johnson. All right, let's say he is on room air, right? And his P little a CO2 is 40 millimeters of mercury, and his respiratory quotient, RQ, is 0.8. And he is at sea level. What is his alveolar air tension? Alveolar air pressure and tension are the same thing. What is his alveolar air tension? This is what I want to know, guys. Fill out this formula using the values I gave you. Mr. Johnson, he's on room air. He has a P little a CO2 of 40 millimeters of mercury. He has a respiratory quotient of 0.8, and he is at sea level. So figure that out. You just plug and pick. Make sure you use parentheses first. Always, just like algebra. It's just an algebraic equation. You done? Oh, okay. I thought you. Go ahead and plug it in. Just bring your P big AO2 down and start substituting. Before you do anything, just substitute. I'll do the first one for you. Y'all looking like, what? But look, you just substitute. Barometric pressure.
Oh, okay.
I didn't say that. I might not have said that. P bar is the pressure of the barometer. Barometric pressure is P bar. pH2O is the pressure of water, right? And I already told you what the pressure of water is normally. So if I didn't give you the pressure of water right here, you use the normal. Okay? Now we do. P big AO2. What's the FO2? I say it's on 1 minute. What is that? 21. He's at sea level, right? He's at sea level, so what's P bar? When we say the barometric pressure, add all these pressures up and add up to what? Wait. 21 is outside. See? Follow the equation. Start point 21, and then you're going. Good. Yeah, just solve it. 60 minus what's the pressure of water? I didn't give you pressure of water, but what? 47. Minus what's the P little a CO2? 40. Divided by what's the RQ? 0.0. That's all. What's in parentheses first? Where is that at? Right here? Yeah, that's mine. I'll scoot it over for y'all a little bit. Minus the P little a CO2 divided by the RQ. Yeah, just like I solving for P big AO2. Then multiply. Then do your division. And then your subtraction. My dear Aunt Sally. Mm-hmm. All right. So I'll give you another minute, and then I'm gonna solve it. You know, I want everybody to watch me solve it, so you can see the process, and then we can do one or two more, and then go on with the notes. And these are normal values that I'm using. This like the 47 millimeters of mercury is the normal water pressure. The P bar is always 760, right? A PCO2, we said less than 35 was hyperventilation and greater than 45 was hypoventilation. It's too much, right? And so the middle is 40. 35 to 45 is the normal PCO2, but 40 is right smack down the middle, right? Perfect CO2 is 40. So that is, and then 0.8 for respiratory quotient is the normal respiratory quotient. So you're going to get, in a healthy adult breathing room air, what the pressure of oxygen is in the alveoli, the normal. You're going to get the normal answer. And that changes when FO2 changes or the CO2 changes or whatever, different sea levels, that can change it. What you're doing right now, guys, is the normals. If you're on Miss Thomas, if you have an answer, you can put it in the chat or you can tell me what you got. Did you get anything yet, Miss Thomas? I don't know if she's on, bro.
I am very confused.
What you confused about?
Everything.
Okay. Well, I'm gonna explain it. All right, so let's look at it. Y'all got an answer? 137. 137, what you got? 139. Okay. It's a little high. I don't know where you get that 39 from. Just know that the normal P big A O2 is about 100 millimeters of mercury. That's normal. Okay. Now, I don't mean this came out like that, but that's the normal. Okay. Now let's work it out. Hello? This is he. Okay, yeah, we'll call you back. I'm in the middle of teaching. All right. P big AO2. So P big AO2 equals, what's the FO2? 0.21. You have to bend it to decimal. 0.21 times, what's the P bar? 760 minus, what's the pressure of water? 47 minus, what's the CO2? 40 divided by, what's the respiratory quotient? 0.8. You got that far, Ms. Thomas?
Yes.
Okay. So now we do what's in parentheses first. 760 minus 47 is 713. So 0.21 times 713 minus. What is 40 divided by 0.8? 50. All right. So now, following order of operations, 0.21 times 713 is what? 0.21 times 713 is what? 149 minus 50 is what? $149 minus 50. How much? 99. 99 millimeters of mercury. There it is. You got that, Miss Thomas? You see how I got that?
Yes.
All right. You see, Ms. Rose?
I don't know what I did first. I think subtract the 713 minus 50, then multiply.
Yeah. No, don't do that. Follow our. So look, everybody, look right here. What we did, we just plug and click first. Just plug everything in before you do anything. The FiO2, he's on room air, 21%, which is 0.21, right? And P bar, he's at sea level, so it's 760. The pressure of water, I didn't give you one, so you use the normal, which is 47, minus his PCO2 was 40, and his respiratory quotient is 0.8. So then I come down. Now I do what's in parentheses first. 760 minus 47 is 713. So I have to bring down to 0.21 times 713 minus 40 divided by 8 is 50. Okay? Now I multiply. 0.21 times 713 is 149 minus 50 is 99 millimeters of mercury. Okay? That is how we solve the alveolar air equation. Okay? So, Mr. Rivers, what we did, we just filled in what we got. 0.21, 760 for P bar, minus 47, minus 40 divided by 0.8. So we came down here. You got to do what's in parentheses first. 760 minus 47 is 713, right? Minus, now 40 divided by 0.8 is 50, okay? So then we bring down to 21. 0.21 times 713 is 149, minus 50 is 99 millimeters of mercury, okay? This? Yeah. Because before you do any subtracting, you need to do that division, right? Gonna knock the division out. All right, so let's look at one more and then we're gonna roll on. Give you a new set of variables. Now, this is Mr. Smith. Smith is at, let's just say, he's on, I got him on 28% FiO2. FiO2. Okay, that's how much he's on. He's not on room air, he's on 28%. Okay, he's also at sea level. Okay, he has a P little a CO2 of 52 millimeters of mercury. Okay, and his respiratory quotient is, let's just say it's 1.2, and his pressure of water, H2O, is 47. These are your parameters here. Okay. Mr. Smith is on 28% FiO2. He's at sea level. He has the water pressure is 47. His PaCO2 is 52, so it's elevated, right? It's greater than 45, so it's elevated. He's hypercapnic right now. And his respiratory quotient is 1.2. I'm just making up numbers. What is the pressure of alveolar oxygen? And all it is, I want to know just what is the pressure of his alveolar oxygen. That's what I want to know. Let me work it out while y'all work it out. When you go, raise your hand, I'll come look at your answer. Ms. Thomas, you can put yours in the chat. If you have an answer, put it in the chat. And it may be a little different than everybody's because there's some decimals in there. I didn't tell you how much to round to and all of that. Just whatever you did should be close. Following the process. Good, Ms. Thomas. Okay. One. All right, so Mr. Rivers, you want to do it on the board for us? Right. Get a little confidence. All right. Yeah, you want to put on camera? I'll do it right here. You can do it right there. You can move it over there. Huh? So then you can move it over there. Move what? You don't want to work it out on camera. You don't want to work it out on camera? Okay, go ahead. All right, so Mr. Rivers is going to work it out on the board, and we're going to look at his work. So here's his work. All right. The answer should be 156 millimeters of mercury. You might have got a point something or whatever. That's fine. But this is what he did. He said he was on 28%, so it's 0.28 times 760 minus 47 minus CO2 of 52 divided by a respiratory quotient of 1.2. He came down, did what's from parentheses first. 760 minus 47 is 713. Brought down his 28 and then went ahead and did the division. 52 divided by 1.2 is 43.3. Okay. Now, what this is the line. He needs to do the multiplication first. 0.28 times 713 is 199.64 minus 43.3 is 156.34 millimeters of mercury. This is the pressure of oxygen inside of Mr. Smith's alveoli. Okay? Excellent. All right, last one. And Ms. Rose is going to work this one out for us. And then we're going to move on. So now we're going to have that alveolar equation down packed. So when we get to it, it's not a shock to you. Okay? All right, let's look at the next patient. Next patient, here's his parameters, the variables. Okay, let's just say Mr. Rose. All right, Mr. Rose is on 30% FiO2. He is at 2 sea levels. Or 2 atmospheres. He's at 2 atmospheres. Okay? We have him down in hyperbaric chamber at 2 atmospheres. Okay? The pressure of water is 47. And his P(a) CO2 is 45 millimeters of mercury. And his respiratory quotient is 0.8. What is his alveolar oxygen pressure? A minute to work that. I'll pause the recording while y'all are working on it. Okay, now we have another student up that's working on my left, about to work out this problem. And we'll see how she got the answer. All right. Yeah. All right, so this is Miss Rose's. And this is correct. So we said the patient was on 30% FiO2. She wrote the formula out first. That's good. So 30% FiO2. Now, the P-bar was 2 atmospheres. So that's 760 times 2, which is 1520. 1520 minus the water pressure of 47 minus the PCO2, which was 45, divided by RQ, which was 0.8. So she went ahead and did that part. 45 divided by 0.8 is 56.25. Okay? Bring down another level. Now, 1520 minus 47 is 1473. Okay? So 0.30 times 1473 minus the 56.25. Okay? Now do this multiplication first. 0.30 times 1473 is 441.9 minus 56.25 equals 385 millimeters of mercury. Ms. Thomas, you see what you did wrong?
I had all of this stuff correct, but I think the calculator on my phone messed up, and that's why I got such a high number.
Yeah, okay. I thought that's probably what it was. Those decimals. All right, so that's how, but so you understand what I just did, what you just saw.
Yes.
That is the alveolar air equation, guys. That's telling us how much pressure of just oxygen is inside the alveoli, right? I don't want to know about nitrogen. I don't want to know about argon or the poots, right? I just want to know how much pressure of oxygen is inside of the alveoli. And to know that, I have to subtract all that stuff. I have to get rid of the CO2. I have to get rid of the RQ. I have to get rid of the water pressure, okay? And so that's how you do it, all right? So let's continue on. It is 10:45. Let's take a 15-minute break. Come back at 11 o'clock, and we're going to finish out. It's not that much that we're going to do today. Finish out some more notes, and then we'll be out of here, okay, for today. Come back at 11 o'clock. Taking a break till 11 o'clock. All right. So continuing on, see the PowerPoint?
Yeah.
Okay. Continuing on, we talked about the Graham's law. We talked about the rate of diffusibility. Carbon dioxide, CO2, is 20 times more diffusible than oxygen, and carbon monoxide is 200 times more diffusible than oxygen. So, excuse me, hemoglobin's affinity, or also known as love, for carbon monoxide is 200 times more than for oxygen, okay? Now, the second way that oxygen is transported is combined with the hemoglobin. We just learned the formula for dissolved in the plasma, which is 0.003 times the P(a)O2. That's how much, and that's expressed in milliliters. When you write your answer, that's in mLs, okay? And then the second way that oxygen is transported is combined with the hemoglobin. We learned in cardiac A&P that the hemoglobin is in the red blood cell, and it is a structure that attracts oxygen molecules, right? That's why you have to have a proper iron in your blood, because that's metallic. It's attracting properties, okay? Magnet properties. And they attract oxygen, okay? And this is the most way that oxygen is transported, combined to the hemoglobin. So out of the two ways, the one that carries the most oxygen is combined with the hemoglobin, okay? The hemoglobin carries the most oxygen to the tissues. Now, hemoglobin doesn't exert a gas pressure, okay? It's just an amount. But how we do, this is the formula here for combined with hemoglobin. It is 1.34 times hemoglobin times the SAT. That is the formula for the oxygen that is combined with the hemoglobin. 1.34 times hemoglobin times SAT. All right. And then the total oxygen content is just add the two together, okay? You just add the two together. So write that down, 1.34 times hemoglobin times SAT. Now the SAT is what you see on your finger probe. The SAT is what you see on your finger probe or on the monitor. How much are they SATing? And that is a percentage which must be put into a decimal before you do anything with it, okay? All right, so let's just do a quick look. I'm not going to work a bunch of these out. I'm just going to do a quick look of the formulas thus far. This is the alveolar equation right here. All right, dissolve in plasma is 0.003 times the P little a O2. That's the formula for dissolve. Dissolve equals 0.003 times the P little a O2. That's the amount of oxygen that is dissolved. All right, combine with the hemoglobin is 1.34 times the hemoglobin times the SAT. That's the formula for combine. Now, you're going to have to get the hemoglobin from a CBC, right? When they draw the CBC, it's going to say what the hemoglobin is. Remember, we said the normal hemoglobin is what? What's the range for hemoglobin? 12 to 15 grams. So whatever it is, you put it there. Okay? Their SAT is what you see on the wall. They sat 95%, they sat 100%, or they sat 80%, whatever it is. You put that there for the SAT, but it must be as a decimal. So if they're satting 95%, then when you put the formula, it's 0.95. And then the total O2 content is C little a O2. C little a O2 is the formula for total oxygen content. And if they couldn't see it. C little a O2 is, now you see this, right? But I'm gonna put this on this board because I'm running out of room. The total oxygen content is C little a O2. C little a O2 is simply 0.003 times the P little a O2 plus 1.34 times hemoglobin times the SAT. That's the total amount of oxygen in the blood. That's how we find the total oxygen content of human blood. This is dissolved, right? So this would be dissolved. And this one would be combined with hemoglobin. And this is the most, right? Combined with the hemoglobin is the most way that it's carried, right? It's carried this way the most. All right. So if you have these formulas, okay, you have these formulas. I'm going to ask us a couple, and we're going to move on because I mean they're pretty much straightforward. You can do algebra, you can do these problems. All right, so let's look at one. I got to erase, so I hope you wrote them down. Write those formulas down because I got to erase. I don't have much room. You got them? Okay. You got them, Ms. Rose? All right. Ms. Thomas, you got them wrote down?
Yes.
Okay. All right. So with that being said, I don't know why I said it. I'm going to stand on you. I can't stop. All right. So for instance, let's just say Mr. Smith has a P little a O2 of 85 millimeters of mercury, that's the pressure, right? And he also has a hemoglobin of 15 grams. His SAT is 96%. And okay, so I want to know how much oxygen is dissolved in plasma, which is in mLs. How much is combined with hemoglobin, and that is in volumes percent. That answer is always in volumes percent. And then total O2 content is also in volumes percent. Work those out with the formula that you know. How much, if his PaO2 is 85, you got an ABG, his PaO2 was 85, you got a CBC, his hemoglobin was 15, you looked at the monitor, he's satting 96%. So how much of that oxygen is dissolved in his plasma, how much is combined to his hemoglobin, and how much is the total? All right, I'm gonna work them out too. Have your three, I'll come on and look at it. Ms. Thomas, when you have your three, you can put your three in the chat. Make sure you have the correct suffix or unit of measure. Dissolved is in milliliters, combined with hemoglobin is in volume percent, and total O2 is also in volume percent. And yes, the dissolved in the hemoglobin is going to be a small number. Yes, very small number. You thought it was going to be a small number? Oh, well, what's the formula for dissolve? So we do 0.003 times 85. No, I said dissolved is a small number. Oh, okay. Yeah, dissolved is a small number, it's a decimal. So let's look at them. Dissolved in the plasma. So that should be 0.003 times PaO2, which is 85. That answer should have been 0.255 ml. Okay? All right. Combined with the hemoglobin should be 1.34 times hemoglobin, which is 15, times the SAC. As a decimal should be 0.96. When you multiply that out, you get 19.29 volume percent. All right. And then total is just add the two together, which is 0.255 plus 19.29, and you get 19.55 volumes percent. Okay. All right, last one. We're gonna roll on. Unless you have a question about it. You feel confident about it? That's the luxury of being live or in the classroom, because you can ask me. If you're not live, I don't know when to stop or start. All right. So let's look at it. Mr. Smith came back, and now his PaO2 is 100 millimeters of mercury. His hemoglobin is 12 grams, and he's statting he's statting 99%. How much is dissolved in his plasma? How much is combined with his hemoglobin? And how much is his total O2 content? I know when you're ready. All right. Good, Ms. Thomas. So here we go. We can move on. Dissolved amount should be 0.3 ml. Combined with the hemoglobin, 15.91912, whichever. And then total O2 content is about 16.22 volumes percent. Now these numbers are important, guys, because we're going to start talking about tomorrow. We'll be talking about hypoxemia, and hypoxia when there's a lack of oxygen. And we got to know, well, what levels constitute hypoxemia, right? And you're going to learn you got mild hypoxemia, you have moderate hypoxemia, and you have severe. Okay, and you're going to learn what those numbers are when it becomes mild, when it becomes moderate, or if it becomes severe. We can do that from the total O2 content. We can do it from the P(a)O2, right? Or we can look at the saturation on the wall. Okay, all three ways can tell us if they're oxygenating or not. All right, so let's finish up for the day. Yeah, go ahead. That's fine, because I mean, it's like some of them have a longer decimal, and some people just go to a couple decimals, and that's all. Yeah, you're still right. All right. So let me share my screen back so we can finish up for the day. All right, so that is combined with hemoglobin. Don't forget, two ways that it's transported. The way in which the most of it is transported is combined with the hemoglobin. Okay, don't forget that. All right, the oxyhemoglobin dissociation curve. There is a curve that is, and I think it's also in your module. I have a picture of the curve. It's in your reading. But the curve is sigmoidal, like S-shaped, due to the hemoglobin's affinity for oxygen at each of the 4 binding sites. Remember, we said hemoglobin has 4 sites that it picks up oxygen. Boom. So it's floating around. Whenever it's around oxygen, it attracts those 4 molecules of oxygen. Okay? In the steep portion, we have minimal changes in PO2, what cause drastic changes in the saturation and total O2 content. One number that you need to know is called the P50. Make sure you highlight this. The P50 is the point at which hemoglobin is 50% saturated with oxygen, and it's normally a P(a)O2 of 27 millimeters of mercury. The P50 is the point at which hemoglobin is 50% saturated with oxygen, and is normally a PaO2 of 27 millimeters of mercury. Okay, now this hemoglobin, or this curve, shifts. Okay, we have some things that make it shift to the left, and we have some things that make it shift to the right. Okay, a shift to the right causes a decreased affinity for oxygen, resulting in a decreased saturation, but increased O2 to the tissue. Now, we're talking about hemoglobin and the tissue. Now, if hemoglobin is floating around but loves oxygen and won't give it up, then the tissues are going to suffer, right? If the tissues say, "Well, my oxygen at? I ain't giving it to you," right? So that's what it's saying. You have a decreased saturation, but increase to the tissues when it don't like oxygen. So right release, say that, right release. A shift to the right causes a release of oxygen from hemoglobin, right? So the hemoglobin lets it go to the tissue. So when it shifts to the right, you have a decrease in saturation of the hemoglobin, right? Because it gave it up. The tissue said, "Well, my oxygen." So here you go. It gave it up. So you have a decreased saturation for the hemoglobin, but the tissue's oxygen increases because you just gave it to it, right? And so these are the factors. What are all things that I tell you, or I'm telling you, that cause it to not want oxygen? Remember I said if CO2 come around, what happens? It drops oxygen and picks up CO2, right? Because it loves oxygen, CO2 more, or 20 times more than it loves oxygen, right? So if oxygen was there, CO2 came over, oxygen got to go, okay? So that's what happened. The factors that shifted to the right. Look at the factors. An increase in CO2. CO2 showed up, so that's going to make me release oxygen. So when it shifts to the right, we have an increase in CO2, an increase in hydrogen ions, an increase in 2,3-DPG, and an increase in temperature. So we talk about that temperature again. So the factors that cause that wave or curve to shift over to the right would be an increase of CO2, an increase in hydrogen ions, an increase in 2,3-DPG, and an increase in temperature. Those are the four things that happen with a shift to the right. So make sure you remember that. I used to say right up, right? Right up. If everything goes to the right, and when it goes to the right, everything goes up. CO2 is up, temperature is up, 2,3-DPG is up, hydrogen ions are up, okay? And we already said a fact about the love that it has for oxygen as compared to CO2 or carbon dioxide. Well, if CO2 is there, guess what? It's going to release oxygen, which means we shift into the right, right? Release, okay? Well, when it shifts to the left, what must be the opposite? Decrease CO2. CO2 left. If he left, don't want to be there no more, then guess who gets picked back up? The good guy, right? Kind of chubby. He ain't really got much, right? But he's the good guy. He's going to pay the bills, okay? So when he's around, hey, you're around. But if CO2 come in there, CO2 fine. So when he comes, everybody got to go. Oxygen got to go, okay? So it shifts to the right and releases oxygen because there's an increase in CO2. CO2 is on deck, so we're going to let go of oxygen, right? We also have an increase in hydrogen ions, increase in 2,3-DPG, and an increase in temperature. These things happen when it shifts to the right. That's disulfide something. You don't have to remember all of that. Just know that there's the increases. Increased CO2, increased hydrogen ions, increased 2,3-DPG, and increased temperature. When it shifts to the right, all these things increase. Okay? Right up. What's up?
Okay.
On this thing, for me, I'm just like that, right? It's saying a shift to the right because of the decrease.
Yeah, a decreased affinity for oxygen, decreased love.
Yeah, but on the thing, it's increased. Everything increased.
Yeah, because when it shifts to the right, everything is increasing. These things, let me show you.
So this should be the left
Let me see what you got.
increase and decrease, right?
So that's a decrease, okay? A shift to the right causes a decrease in affinity for oxygen. Don't love oxygen that much because CO2 is up. Because CO2 is up, I stop loving oxygen. Right? Because CO2 is up, I stop loving oxygen. Okay? So a shift to the right causes a decrease in affinity. That means the love. A decrease in the love for oxygen, resulting in a decreased saturation or decreased petition. So when it shifts to the right, it's because CO2 came over. So when CO2 come over, oh, oxygen got to go. My love for oxygen goes down. Right? And the other things are just a list of other things that are happening with that shift to the right. Okay? So when it shifts to the right, you have an increase in CO2. That's the reason why it went to the right. Okay? You also have an increase in hydrogen ions. You also have an increase in 2,3-DPG and an increase in temperature. Okay? So when CO2 come around, all these things happen. It shifts over to the right and releases oxygen. Right? Releases. Left loves. Right releases, left loves. Okay? So the curve, like I said, I'm gonna show you a picture of the curve. It's sigmoidal. It's kind of like an S shape. It can either be normal, it can shift to the right or it can shift to the left. When it shifts to the right, that causes a decreased love for oxygen. The reason why it shifts to the right is because CO2 came around. Because remember, we're talking about the hemoglobin's love. Hemoglobin loves CO2 20 times more than he does oxygen. So if I'm normal and everything's fine, but then CO2 come over, I'm going to not love oxygen no more. I'm coming over with him. Okay? And when she comes over to CO2, she releases oxygen. Okay? She gets rid of it. You got to go. And then when CO2 leaves, you can come back. Okay? So let's look at the left. Now, a shift to the left causes an increased affinity for oxygen, which results in a decreased CO2, a decreased hydrogen ions, and a decreased temperature, and a decreased 2,3-DPG. Shift to the left, loves. So say left, loves. Left, loves. Left, loves. Okay? So a shift to the left causes an increased love for oxygen, resulting in an increased saturation of the hemoglobin, but a decreased saturation to the tissues because it won't let it go, right? Hemoglobin is floating around, but won't let go. It's like, put it like this. Say you got a favorite teddy bear, and you got a whole bunch of kids in the house, right? That little kid is walking around with that. He won't let it go, right? Because he loves that teddy bear, right? And so he won't let it go. So y'all just asked out, right? You ain't going to get this teddy bear because I love this teddy bear. But you bring Buzz Lightyear in, he's like, ooh, Buzz Lightyear. Boom. Drop the teddy bear, right? And picks up the Buzz Lightyear, okay? That's the same thing that hemoglobin is doing. It's walking around with oxygen, right? And when CO2 come around, it decreases its love for oxygen. He puts that oxygen down and picks up the CO2, okay? When that happens, everything is going up. The CO2 has gone up, the temperature goes up, the DP3 goes up, and the hydrogen ions go up with that shift, okay? Well, then when CO2 leaves or the Buzz Lightyear stops working, well, here, I drop the Buzz Lightyear and pick up oxygen again. I'm satisfied with that, right? And then everything goes back down. So somebody, let's say somebody on the down low, okay? Down, low, left, down, right? Down, low, okay? That's how you remember. To the left goes down, to the right, up, down, low, all right? Right up, down, low. You can remember like that, or you can say left loves, right releases. Either one that helps you is fine, okay? So a shift of that curve to the left causes an increased love for oxygen, resulting in an increased saturation for the hemoglobin, but decrease to the tissues because you won't give it to the tissues. The hemoglobin won't release it because it loves it, all right? Takes a little minute for you to just read about it and keep saying it to yourself. You'll get it, okay? You'll get it, all right? So I'm going to show a picture of the curve, and then that's going to be it for today. I'm going to show a picture of the curve, okay? What y'all need to know is what happens when it shifts to the left and what happens when it shifts to the right. So when it shifts to the left, everything goes what? Those four things. See, down. CO2 go down. Hydrogen ion go down. Temperature goes down. 2,3-DPG goes down when it shifts to the left. When it shifts to the right, everything goes up. CO2 is up. Temperature is up. Okay? That's the basic that you need to know. And when it's in the middle, that's the P50. Right? P50 is when it's right 50% saturated with oxygen, and you're going to see the graph here in a second. All right, so that is, like I said, that's the oxygen hemoglobin dissociation curve, which I'll show you a little bit more. Let me find I think it's in the module. I think it's in the module. I think I put a picture of it. If it ain't in your note-taking guide, then I definitely know I put it in this module. I swore I did. So yeah, hemoglobin, it says O2 hemoglobin curve document. I don't know what this service unavailable stuff is, but you just hit it and download it and open it up. And I'm gonna share my screen to it. Here we go. All right, guys, this is the O2 dissociation curve in a nutshell. All right, hemoglobin dissociation curve. Can you see it? All right. Look, shift. What? I'm not trying to minimize. Okay, here we go. Shift to the left, which is an increased love for oxygen. Okay, left loves. Means there will be a higher oxygen content for any given PO2. And the shift to the right is a decreased love for oxygen. So right releases, left loves. Got that? This is the curve here. In the middle, guys, this is the normal line. This is normal. The hemoglobin curve is normal. This is a shift to the right, and this is a shift to the left. See that? Shifts over to the right, or it shifts over to the left. Look at the P50. This is the saturation over here. You see this 50? The P50 is the point at which the hemoglobin is 50% saturated with oxygen, right here. And the PO2 is at the bottom. So what does this match up to? P50 is right here, and it matches up to a PaO2 of about what? Well, this is 30, so I think it's 27. 27 millimeters, so that's a fact, okay? And that's what they're trying to show you. This is the oxyhemoglobin curve here. The middle line is normal, okay? Normal. You can either shift over to the right or it shifts over to the left, okay? So look right here. When it shifts over to the right, decreased affinity, okay? You have increased levels of temperature, 2,3 dpg, CO2, right? All things go up when it shifts to the right. CO2 is up, temperature is up. High levels of 2,3 dpg, they're up with the shift to the left. To the right. Now go back to normal. Now let's shift over to the left. Left loves oxygen, so everything else goes down. Decreased CO2, decreased temperature, and low levels of 2,3 dpg. So you see that? Y'all see the normal right here? This is to the right, this is to the left, okay? Now, that's one thing you need to know, is what happens when it goes to the left or the right, okay? Now, let's look at the 50. This over here is the percent saturation, okay? This is the percent saturation of the hemoglobin. At 50% saturation, look at the line. The line goes over to here to the middle line. This is the point called the P50. The P50 is right here. This is the point at which hemoglobin is 50% saturated with oxygen, okay? Now, what is the PaO2 that corresponds with this P50? Because PaO2 is at the bottom. About 27, okay? What if it was shifted over to when it shifts over to the left? What is the PaO2 when it shifts over to the left? What is that about? About 32. See that? What about if it was to shift over to the right? Right here in the middle. Shift to the left gives us a PaO2 of what? 20, right? Gives us a PaO2 of 20. What about when it shifts over to the right? What is that PaO2 about? About 32. Okay, no exact number except for that 27 that they tell you. Okay, so that's what they're trying to show you. A shift to the left loves oxygen. Okay, so because it loves oxygen, it's not releasing it. So the PaO2 goes down. See, the PaO2 is 20. That's the pressure of oxygen. It's lower because hemoglobin won't let it go. All right, but when hemoglobin releases it over to the right, then the PaO2 goes up because now it's releasing it to the tissues and it's not holding on to it, okay? So all you need to know about the oxyhemoglobin curve, guys, is it's a sigmoidal curve and it signifies the love for oxygen at any given point. When this curve right here, look, this is the curve. This is the normal point. When it goes over this way to the left, a shift to the left loves oxygen. You have it loves oxygen and you have everything else goes down. CO2 went down, temperature goes down, 2,3 dpg goes down, okay? Now let's go back to the middle. What happens when it shifts to the right? We have a shift to the right, then everything does what? Goes up. CO2 goes up, temperature goes up, 2,3 dpg goes up. Now this acidosis and alkalosis, we're gonna learn that a little bit later when we get into those numbers, and then you'll understand that's the hydrogen ion there, okay? Because you gotta understand hydrogen ions is the pH. That's your pH. The lower your pH, the more acidic you are. The higher the pH, the higher it is. Like alkaline water, we want water with a higher pH than regular water, right? That becomes alkaline. And so there's going to be a fight, a battle between acidosis and alkalosis, okay? The body wants to be smack dab in the middle to keep pH. If my head is pH, my head kind of goes with who's causing me to do it, right? And the two forces are CO2 and bicarb. What's the normal bicarb? Normal bicarb. That was one of the electrolytes we talked about. Bicarb.
1.5 to 2.5
Oh. Normal-
milliequivalent per liters.
No, bicarb is 22 to 26. 22 to 26. The HCO3. Yeah, that's part of the electrolyte. That's in your electrolyte list. HCO3. That's part of your electrolytes in the lecture for sure. But it's in your lecture. We talked about it in the PowerPoint. Bicarb is 22 to 26. 22 to 26 is the bicarb. 22 to 26. But I'm just telling you that now to tell you that that's part of the two opposing forces. Bicarb and carbon dioxide. Bicarb and carbon dioxide. So look right here, I'm gonna share my screen. This is the lecture that we did right here. Everybody see my screen? Electrolytes, sodium, chloride, bicarbonate, potassium, calcium, and magnesium. We went over those. Bicarb is 22 to 26. Okay, that's the base, right? That's the Rolaids. The bicarb will be the Rolaids. Okay, and the CO2 is the what? CO2, aka, if we're talking about acid, CO2 is the acid, bicarb is the base. Okay, all right. So that's the curve. Look over the curve. Like I said, what you need to know, guys, about the curve is that when everything shifts, when that curve shifts to the left, it loves oxygen. So hemoglobin won't let it go. It loves it. All right. And everything else goes down. CO2 is down. Temperature down. 2,3 DPG down. Right. Down low. Down low. Right up. Okay. I'll be right up. Right up. Everything's going up. Okay. Now, don't get confused with the affinity and what things are doing, because just because lefty loves affinity, but that's still everything else goes down. Because it loves, everything goes down. And because it don't love, everything goes up. Okay? So don't get that part confused with the things that go down. The love is not part of that. All right? When I say temperature goes up, 2,3 DPG goes up, hydrogen ion goes up, that don't mean the love go up, right? The love is different. That's the first part. If it loves, it goes to the left. And when that happens, everything goes down. If it releases oxygen, it goes to the right and everything goes up. Okay? So you need to look at that to help you understand what's going on. Because we said because of Graham, he says they diffuse much better. The CO2 crosses that barrier 20 times faster than oxygen does. Okay? And carbon monoxide crosses that barrier how much faster? 200 times. 200 times. That's a lot. And so because they are so much more diffusible, then that is what marks the relationship between the hemoglobin and the CO2. Okay? Only because it can go across so much faster. So when he come around, she can't help but to pick him up because oxygen you took too long, right? When both of them are coming, it's going to pick up the oxygen. I mean, the CO2 before it does the oxygen because it gets through faster, right? Whoever gets in the door first is who wins, right? And so that's what's happening, guys. Shift to the left, it loves oxygen, and those four things go down. A shift to the right, it releases oxygen, and those other four things go up, okay? All right, so do your reading, do your studying. We will get back into this tomorrow. The homework, you don't have any homework for tonight. All I need you to do is study. If you took the test today, then you have credit for today as far as attendance is concerned, because you took the test, okay? And so because you took the test, you have attendance for the day. There is no homework, so don't worry about that. I will see you guys tomorrow, same time. We will continue on with our lesson. Feel free to go ahead in the PowerPoint and kind of read it a little bit. And so that you have a little understanding, or you have heard it when I talk about it tomorrow. Those alveolar air equation, play with it, okay? Play with those, give yourself some numbers and work them out so you understand how to work all of those formulas. You need to know dissolved, you need to know combined, you need to know total, all right? You may come tomorrow and I give you a pop quiz on just a few things and say, okay, work this one out, work that one out. So be sure to study those formulas, okay? Because all we talked about is 2 ways to transport oxygen and the hemoglobin curve. That's all we talked about along with those formulas, okay? So study that tonight, be ready or be prepared to talk about them or work them out tomorrow during class, okay? Have a good day. Good job today on the test. I will see y'all tomorrow.